Welcome to this video where we explore the half-wave rectifier signal, one of the fundamental building blocks in power electronics. In this video, you'll learn how a half-wave rectifier works by allowing only one half of the AC waveform to pass through, effectively converting AC to DC. We'll walk you through the key components and visuals that make understanding this concept easier. Firstly, the formula overview, where we will have a clear look at the mathematical expressions that describe the rectifier's behavior. Second, the Simulink model, where a simulation setup in Simulink is used to visualize signal flow and system response. Third, the MATLAB analysis, where code-based exploration to support the theory with data and plots. Then, the actual implementation pictures, where we will present the real-world images of the physical circuit and setup. By the end of this video, you'll have both the theoretical understanding and practical insights into how a half-wave rectifier functions. Now, let's dive in. Now, let's take a look at the three Fourier series forms of a half-wave rectifier signal. Firstly, the exponential. Then, we have the trigonometric. And then, we have the combined trigonometric. Let's proceed to the Simulink models.
What's up guys, in this video, I will show you the simulation of half-wave isotropic rectifier with resistor and RL load using MATLAB Simulink. First off, I will insert AC voltage source block. This provides the alternating voltage that needs to be rectified by the circuit. Then the second is the diode block. The anode of the diode connects to the positive of AC voltage source. This allows to pass only in one direction block the negative half cycle of the AC voltage, enabling rectification. Next is the RLC branch block. But in this case, we won't need the inductor and capacitor, the resistor, half-wave rectifier, but later on I will use inductor for RL load. The resistor acts as a load in the circuit. One end of the resistor connects to the cathode of the diode, and the other is connected to the ground of AC voltage source. The circuit is now completed. Now we're going to put measurement blocks in each blocks. The first input voltage measurement block allows observation of input waveform to compare it with the rectifier input output. Then the diode voltage block helps us analyze the diode operation by showing the voltage drop across it during conduction and non-conduction phases. Lastly, the output voltage measures the final output voltage across the load to observe the rectification effect. We will now insert a scope block. We will now connect each measurement blocks in the scope block. Scope block is for the visualization of rectified waveform in the Simulink for analysis and rectification. Finally, to complete all the needed blocks, we need to put power GUI block. This initializes the electrical states of the model and allows the scope to visualize waveform. This time, we will now change the parameters of each block. First, the AC voltage source. The peak amplitude has an RMS value of 120 square root of 2 with a frequency of 60. Then, in the diode block, we won't need to change the values except the forward voltage of the diode, which commonly the silicon diode has 0.7 forward voltage. And we won't need to show the measurement port, so we're going to disable it. In the resistor load, I will use 100 ohms. Now, we are going to change the time step in 0.04 and run the system. Finally, we're going to watch the signal generated in the scope. As you can see, the input voltage is continuous sine signal, and the signal in the diode is the negative half cycle of the input signal. And in the signal in the load is the positive half cycle of the uncontrolled rectifier. You can change anytime the parameters according to your preference. Now, we're going to change the resistor with RL load. So, I will use an inductance of 100 microfarads. 100 microhenries, I mean. Then run again. As you can see, this is the signal output. That's all for today. Thank you for watching.
This model is designed to convert an input signal into a controlled DC output using a thyristor. Unlike a regular diode rectifier, here we have control over when the rectification begins, which is useful for applications like dimmers and motor speed controllers. I will be explaining the components and their functions. First, we have an AC voltage source that provides a sinusoidal input with peak amplitude of approximately equal to 169.7 volts, frequency equals to 60 Hz, and a period of 1/60 seconds. This is the input that we want to rectify. We have two voltage measurement blocks. Before the thyristor, which is to observe the AC input voltage, and across the resistor, which is to measure the rectified output voltage. Thyristor, which is an SCR or a silicon-controlled rectifier. The thyristor acts as a switch. It remains off until it receives a gate pulse, then it stays on until the current naturally drops to zero. This allows us to control when the rectification starts. Pulse generator. This block generates a triggering pulse for the thyristor at a specific phase delay. The delay is set to the period times 61.2 degrees divided by 360 degrees seconds. This means the thyristor will start conducting at 61.2 degrees into the positive half cycle. The current measurement block. This measures the current through the load resistor so we can analyze the rectified current waveform. The resistor with a resistance value of 100 ohms. This is our load which receives the rectified power. Since it's purely resistive, the voltage and current will be in phase. Finally, the scope captures and displays the input voltage, output voltage, and load current waveforms. This helps us visualize how rectification is happening. Last, the power GUI block. This is required for Similink's electrical simulations. It ensures our circuit runs correctly in the continuous domain. Now, let's understand how rectification occurs in the setup. First, at the start, the thyristor is off so no current flows. Second, the AC voltage begins its positive half cycle. Third, at 61.2 degrees, the pulse generator triggers the thyristor, allowing current to flow through the load. Fourth, the thyristor stays on until the AC voltage crosses zero. Fifth, during the negative half cycle, the thyristor stays off, blocking current flow. Sixth, this process repeats every cycle, producing a controlled rectified waveform. So what do we expect to see? The input voltage, we'll see a standard sinusoidal AC waveform. In the output voltage, we will see a rectified waveform that starts conducting at 61.2 degrees and continues until zero crossing. And finally, the load current, we will see a waveform similar to the output voltage since I is equals to voltage over resistance. This type of controlled rectifier is widely used in dimmers, adjusting light brightness, motor speed controllers, controlling speed by adjusting power input, and DC power supplies, providing variable DC voltage from an AC source. And that's how our half-wave controlled rectifier works. We saw how each block contributes to the simulation and how the thyristor provides control over rectification.
The half-wave uncontrolled rectifier with C filter is a basic power electronic circuit that converts AC to DC using a diode for rectification and a capacitor to smooth out ripples. This circuit is commonly used in low-power applications like battery chargers, power supplies for small devices, and signal demodulation where pure DC is not required but ripple reduction is essential. Today, we are going to show half-wave uncontrolled rectifier with C filter using MATLAB Simulink. Let's break down the circuit. Here is the AC voltage source. This provides the AC signal input, which is typically sinusoidal with a specific amplitude and frequency. In this case, the peak amplitude is approximately 169.71 volts, and its frequency is 60 Hz. The next is the diode or the uncontrolled rectifier. The diode is responsible for converting AC to DC by allowing current to pass during the positive half cycle. During the negative half cycle, this diode blocks the current, resulting in a pulsating DC output. Next, we have the capacitor or the C filter. The capacitor is placed in parallel to the resistive load to smooth out the pulsating DC. During the positive cycles, the capacitor charges to the peak voltage, and during the negative cycles, it discharges slowly, providing a more consistent DC output. This filtering process significantly reduces ripples and improves the quality of the DC output. The next part is the resistive load or the resistor. This is the part of the circuit where the converted DC power is utilized. It receives the rectified signal from the diode. The current measurement block. This measures the current through the diode and capacitor to monitor charging and discharging. The voltage measurement block. This measures and compares the input voltage from the AC source and the output voltage across the resistive load. The scope. The scope is used to visualize the output waveform of the rectifier. The power GUI block. This block is essential for running simulations, particularly when dealing with power electronic circuits. It provides simulation, control, and analysis tools, allowing us to accurately observe and analyze the circuit's performance. So this is how the circuit works. The AC voltage source supplies an AC signal to the circuit. This signal is sinusoidal and alternates between positive and negative cycles. Now the diode plays a key role. During the positive half cycle of the AC signal, the diode becomes forward biased, allowing current to flow. This is where we get a pulsating DC signal. During the negative half cycle, the diode is reverse biased, blocking the current and effectively turning it off. Here's where the capacitor filter or the capacitor comes into play. It's connected parallel to the resistive load and does an amazing job at smoothing out the signal. When the diode is on, the capacitor charges up to the peak voltage. As the input voltage starts decreasing, the capacitor gradually discharges, providing a more stable DC output. The resistive load or the resistor receives this filtered DC signal, which is much smoother than the original pulsating DC. To analyze our circuit, we use the voltage and current measurement blocks. The voltage measurements are taken at the AC source and across the resistor to compare the input and output signals. The current measurement block is placed in series with the diode and capacitor to observe the charging and discharging process. We can see the multiple waveforms in the scope. The first waveform displays the input voltage, that's your pure AC sine wave. The second waveform shows the output voltage, which is the rectified and filtered DC signal. The third waveform shows the diode current, which tells us when the diode is conducting or blocking current. So we can see three waveforms. This waveform shows the input voltage, a pure AC sine wave coming from our AC voltage source. This is then the output voltage. This is the rectified and filtered DC signal after passing through the diode and capacitor filter. And this one is the diode current, which indicates when the diode is conducting or blocking current during AC cycles. The half-wave uncontrolled rectifier with C filter is commonly used in battery chargers, converting AC to DC for charging batteries, signal demodulation, extracting useful signals from modulated carriers, DC power supplies providing low-cost DC power for small electronic devices, and voltage measurement systems used in analog voltmeters for converting AC to DC for easier measurement. We can see how the simulation effectively demonstrates how the half-wave uncontrolled rectifier with C filter works. By using a simple capacitor filter, we can significantly improve the quality of the rectified signal. Now let's talk about the 6 fundamental transformations you can apply to a signal. These transformations help us understand and manipulate waveforms in signal processing and system analysis. The 6 transformations are time reversal, time scaling, time shifting, amplitude reversal, amplitude scaling, and amplitude shifting. Time reversal, also called horizontal flipping. Here, we reverse the direction of time, which reflects the signal about the vertical axis. Time scaling is the transformation which compresses the waveform in time, making it oscillate faster. Time shifting moves the signal from left to right. It delays the waveform by pi over 2. Amplitude reversal, also called as vertical flipping, is where we multiply the signal by -1. It flips the waveform upside down. Amplitude scaling changes how tall or short the wave is. It doubles the signal's amplitude. Then lastly, we have amplitude shifting, which moves the waveform up or down.
Previously, we simulated the uncontrolled half-wave rectifier. Using the original circuit, I will now show you how we will modify our half-wave rectified signal into 6 different transformations. The first transformation is the amplitude reversal. I will show you the 2 ways. First is we're just going to get the reverse bias of the diode to get the negative half cycle. As you can see, the signal flipped into the negative side. And the other one is just inserting a negative gain block after the half cycle. As you can see, it also ends in the same result. The second transformation is amplitude scaling. Simply in the definition of amplitude scaling, the amplitude of the signal is just simply amplifying the voltage of the signal. To do this, we'll just add a gain block and set it to any number greater than 1. So I'll be using 2. As you can see, the amplitude of the signal is twice as the original. Fifth transformation is time signal. Unlike the previous transformation, it is more challenging because we're going to arrange the circuit but still come up with a half-wave rectified signal. The components rearranged where the AC signal is fed, which is here, is fed to anode of the thyristor. And the square wave will serve as firing trigger to the gate. Then the cathode will be fed up to the RL load parallel to the diode. So I'm going to run this code. We can see the oscilloscope delay of the half-wave rectified signal. We're moving to the first transformation, which is time scaling. To do this, we're just going to add a frequency to the AC signal. We can actually see the changes if we use only one AC signal. So to visualize, I added another AC signal, increased frequency to 65 Hz. So we can see that the frequency increases while the wavelength decreases. Transformation is time reversal. In time reversal, we can't actually show in the oscilloscope because scope only read a real-time signal, meaning it can show us the negative time because there is no such negative time. If we wanted to visualize the time reversal of half-wave rectified signal, we're just going to flip the original signal to the left.
We now have a MATLAB simulation, where a GUI was created to showcase the 6 transformations.
Shown before you is a MATLAB GUI program which demonstrates how different signal transformations affect a waveform known as a half-wave rectified signal using Fourier Series approximation. This GUI provides interactive controls to experiment with different signal transformations. When we run the code, a window opens titled HWRS Transformations. These are the elements in the GUI. On the left, we have the input signal parameters. A for amplitude, F for frequency in terms of hertz, N for number of harmonics used in the Fourier approximation, A for time scaling factor, P's of O for time shift value, A prime for amplitude scaling factor, and B for amplitude shift value. And on the right, we have the 6 checkboxes that allows us to apply time reversal, time scaling, time shifting, amplitude reversal, amplitude scaling, and amplitude shifting. And in order to visualize the result, there is the plot button. When we click the plot button, the app constructs a Fourier approximation of a half-wave rectified sine wave. Shown is the Fourier series we've used in order to approximate the half-wave rectified sine wave, where A is the amplitude, W is the angular frequency, which is equal to 2 pi f, and N is the harmonic index from 1 to N. In the resulting figure, a red line shows the Fourier approximation of the half-wave rectified sine signal. A dashed black line plots the actual half-wave rectified sine, which clipped below 0. Any selected transformations are applied and plotted as dashed lines in different colors. Each transformation visually alters the signal. The time reversal reflects the signal horizontally. The time scaling compresses or stretches the signal depending on the value of A. Time shifting moves the signal left or right in time. The amplitude reversal flips the signal upside down, and the amplitude scaling stretches or compresses the amplitude. And last, the amplitude shifting moves the waveform up or down. In program code, this function computes the summation part of the Fourier series used specifically for the time reversal case. It's a helper that avoids repeating the same loop. To sum up, this program is an interactive and educational GUI in MATLAB that helps visualize how basic transformations modify the structure of a periodic signal. It's a great way to build intuition about signal behavior. Shown are the pictures of our actual implementation of the half-wave rectified signal that we got during our laboratory.
And that wraps up our video. We explored the half-wave rectifier signal, broke down its Fourier series representations, and examined the 6 basic signal transformations. We also walked through simulations using Simulink and MATLAB, and took a look at some real-world implementation images to connect theory with practice. Understanding these fundamentals is key to mastering signal processing and system design. Thanks for watching, and don't forget to like, share, and subscribe for more content like this.